So we're going to learn the Landau Fermi-Liquid theory. So Fermi-Liquid theory is the interactive stuff. It's the interacting component, so we need the single particle component, but the different particles will come from each other. So you can know the potential in the particle. So then, so the main idea is that you can approximate this so the system is integral system by non-interactive system. So the idea is interaction. That's the idea of this Landau parameter. But with some renormalized parameters, so that's for one Landau parameter. And that's what we're going to learn. I mean, essentially, it's very similar to what we learned from the IDF, but so we were talking this question. Okay. So what we have is that the main idea of Landau is that if you start with the idea with no interaction, say no interaction, so say let's put that parameter G in here. It's for constant constant usually. And constant constant. When G equals to 0, it's just a usual idea, but G is not equal to 0, actually you get the interacting system. And then Landau's idea is that you start with G equals to 0, and automatically change the coupling content slowly. Then the behavior fermion should be very similar to you can connect between ideas and the interactive system by automatically. So you can describe the system of interactive system by just changing content. And then, so we're in graph-generic ensemble, and what is equal to exponential. Here, and omega 0 minus EQ, like this way. Like this way. So this is the ground potential, ground potential, and then this is the numbering operator. So this is the numbering operator, and then here you just have the EQ and mu for each split. Okay. And entropy is given by minus kb phrase roll up and a slope roll up. Roll up and plug up into here, what you get is a column. The here inequality, so n half n bar q, the expectation value of this. So the number operator, expectation value number operator, which can be understood as a list of row count. dq. So if you put so it's just expression log counter, what you get is this one, and you calculate by row, first trace on row path and the CQ level CQ, you get the number expectation value at each state Q. Q is a sample state. Okay, and then this Q can be understood as the one time. So this is just so this is the usual Dirac distribution or whatever form distribution. Depending on the certain event involved. So from here, we can just show up the. So from here, we can show up the E minus player. So from here you can show that exists. Okay. And also omega naught is given by over there. It's given by over there. So using that one can show that the okay, different sigma. So plug this one over there. And massage it. You can just show up the. Okay, maybe I should do that. Minus sigma and q. 1 plus sigma and q. And there's nothing. And this is sigma inverse. Sum of q plus 1 plus sigma and q and inverse. So therefore, we can just put this one. Okay. So therefore, plug this into q, and we know q bar is this side. And we plug that into q, we can just show the as follows. S and then minus yeah, plus 0 and 3 log and q or just equal to n q. Okay, like this. Yeah, this is that okay? So I just plug this one. If you take a log of this one, you get this one. Okay? Now you just do massage it, you will get as follows. So massage it, you get like this. like this. So this is you can just check from here to here. It's very easy. You just edit. I think you just can do. Okay. So then this is the same as I didn't get it. Okay. So unfortunately, I think a long time ago, like lecture 3 or something, I already showed it. If you forget about it, I'm not gonna drag again for I didn't get game. I didn't get game. We only show this one. So interactive system, even though interactive system, if you use this what operator and so on, one can derive. Okay. And the ground potential of low path is based on raw path. H plus beta inverse of raw path. That's the case. So everything is the operator. So this is essentially what you get is H minus beta inverse S. So that's what you get. So this is ground potential, and you can just use this column to have this. But we do that so we use the something called the block. Okay. Dominis here. For which contrast? Which we show the row 2. Is equal to derived this by root compression. Okay, so and then we can use this to apply the this component. If you use that, we can just obtain as follows: the omega of is sorry. So as I mentioned last time, so it's a Fermi-Liquid theory. So it should have the spin 1/2 at least. It should be like all half of, I think, strictly half integer. It should be whatever spin must be half or whatever, and so on. So it should have a spin. So here, as a breast, you should have a spin variable like alpha 1 or alpha 1 usually, and so on. So I just suppress. I just let it in that. So in the lecture notes, I just write down C is the shorthand notation of this. Okay. 1 second. Okay. So this part is turning into this. Into this one, and yeah. What? Sorry, what I'm thinking. And we already knew. What should what should I do this time? Like this. Okay, so this term coming from, so this line coming from log. The second line, the first and second line is just coming from expression value. So this rate of row calculation. So we just work with it. The only I didn't include this one, and I don't know why I didn't include it. Why? We don't. Sorry. It's okay. It was okay. Sorry. We don't need this time. We don't need to shift. We don't need this. Okay. And now we use the row 1. It's just so we use the part of the element. It's double Q. So from here, the 1 of x1, x2, and written as by q, by q, x2, star, and q. Do you agree with that? Is it okay? Is it okay? And so this is the expectation value style of x1. Sine theta of x2. Okay. And this one is the here, here, like this. Okay. So then numbering operator and is the product of one. Thank you. So here we use the fact of the orthonormal, So if you do the integration on the side of x1, 1/4. So this is equal to okay. Then in equilibrium, so omega has to be stationary, like minimally, equilibrium, minimally. With respect to instant Q or and Q. So therefore, we can take the derivative with respect to and Q. Okay. So then like this way. And this is one particle of the volume. Did I hear? Okay. So and then we have so one. Okay. So this is the and Q derivative is of this guy, either in this guy. So factor of two. I have a factor of two here. Is that either we apply to this side or this side or this side. Then you get the factor of two. And the second guy is the pi star Q. And that's okay. So this like this. And we told us, oh, like fortune and race it so different. So this one, so do you remember this number? I just do you remember? Do you remember? So this is the case. So plug down into here, and then massage. And then what you get is pulse. And then you can massage the peculiar system. Like this thing. And then follow more. And then this one, as a surprise, this is the new. This is called half the top potential. And then the explicit form, I'm going to write it down. Like this. Okay. So that's heart rate for equation. So I just massage this above equation and the equation. Okay. That's what you get. Now we have a very, very nice form. So we can treat this one as Hamiltonian. We can treat this one as Hamiltonian. So essentially what we have is that the and phi q is the Hartel. while Q is the eigenstate. And that stands for the following equation. All the normal terms. That's that case. I mean, if you want precise, I can write down what it is. Okay. Any questions? Okay. So if you plug, oh my goodness. So let's write down the minimum. Okay, so experiment equation of equilibrium is of rho. It's the rho amplitude of report of yeah, that's what okay. So that's what you would question is what? So this part really comes from bracket. Unfortunately I erased it. That's I kind of regret. So this part I used this equation. This equation. So usually something like this. Maybe I should write it down. Um, yeah, maybe. Okay. So yeah, and it's almost same as before. Um, okay, maybe it's okay. Maybe I can use that. So yeah, essentially what we have is that the so raw minimum operator is times three times n cube, and the sum of it, and then standard case. This one is it should be something like and then and like this. So that will be what we have for the and we know so here we can use this equation to get the equal three times and q bar and q bar. And what's left is so there's a difference between factors of here and here. It has to be log up. It has to be log up. We have to subtract this one. Subtract this one. And this part is just S. This part is just S. So S values. S values. Okay, so that's what you get from this analysis. Okay, so then we can count on this one and this one. And plug the expression for rho, and this is equal to like this. Well, how we want the equilibrium of any question of this moment? Any question? Okay. 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 Another derivation for this ground potential for equilibrium can be used with weakly composition. Um, it's the same thing. We have that diagram, like induction. With induction term, it's like this. And then we already learned that the weakly composition can be written as follows. Okay. Okay. So derivation, I think we can better not to write everything. It's going to be boring. So I just write down the important part. So the conclusion is that this can be approximated by the weakly composition. We can just write down as follows. I just write down. So we can use a weakly composition. And like this one is atomic. Atomic is given by atomic is given like this. The plug this into here and it just not touches. And I'm not going to grab everything because it's going to be horrendous. It's just a lengthy calculation. And just give you just derivation. I mean, you just have to different into here. So you just have to take the expression. So you just have to take the expression. Into here. That's it. And then interaction time becomes like this. So the interaction time becomes like this. like this. Okay. And then you can just combine, so this is like color H. I mean, if I do exercise, I mean, I'm not gonna derive step by step. So you can just plug that into here and then compare with this definition of U, algebraic, and then plug into here what they are again. I mean, it's a good exercise. You guys should do that. It's just simple exercise to do that. This is the key. Okay. And then use this equation to rewrite this one, the Hamiltonian in the sample cube. Okay. So the first part of induction term can be can appear here, and that will give you this function. And that is the using cube. Okay. And then what's left is this one. And then you can sandwich. So this is the operator. This is the operator, and then you can just use omega as the base of rho. H hat minus plus log. And then after some constant, you can just obtain this. For example, in fact, very interesting. Very interesting. Okay, so that's the transformation. So the plug this into here, and use the relation of beta inverse of S, and you again obtain the same ground potential. Oh, okay, good. Okay, so that's the definition for interacting system for ground potential. So this is the ground potential for interaction. So yeah. Okay. So as the cost of interaction, you need to add this one. You need to add this. Any question at this moment? So now, using this ground potential, so you can derive lots of some dynamic quantity. To do that, so we will consider homogeneous case. Homogeneous case. Okay. Sorry, so stupid. Maybe before going to that, I think I should mention that other so this is the one I derived. And then also this equation. I don't know why I use this. Sorry, I should add something. So this is a cube of x1. So this equation involve the half inputs. Formula for the whole equation. Okay. So this means that this eigenfunction. So the eigenfunction and the eigenenergy here can be determined by this U-Hartree box. Okay. Once you determine U-Hartree box, you can determine phi q and epsilon q. So U-Hartree box for potential here can be determined that this interaction term, but this rho one is just rho one for x1, x2 is sum of q and then and q like this dot. Okay, so this rho one is also determined by the eigenfunction phi q. Okay, phi q. So therefore, so you have to solve like q to determine phi q, you have to determine U-Hartree form. To determine U-Hartree form, you have to determine phi q. So therefore, this equation just can be solved by like perturbatively. So once you have a perturbation of this U-Hartree form, and you can determine phi q, then plug that one into here, and to get the product function to U-Hartree form, and just plug that one into here, and again solve it. Then you get the next order approximation, and that one can be plugged back into here, and that will give you more precise U-Hartree form. And plug that one into here again, and you solve phi q, and then you get a more precise version of phi q. And then that is called as and this is called a self-consistency equation as well. You can solve the self-consistency. Okay. Okay. So then now we move on to the linear case. So from here, the spin becomes important. Okay? So from here, spin becomes important. So I just bring the notation of the homogeneous spin. So here, the assume the no, sorry, H0 is equal to Dm plus U over 1. And I'm not going to consider this potential for the sake of simplicity. Okay. Then the solution to this one is the so solution of this one is just blank. Which is something like this. Okay. Okay, so then so without interaction, we have rho 1. It's from now on, it's going to be important to have the spin variable. I just replace x1 to the d1. And then you can just write down the outcome. Yeah, so this oh yeah, sorry, I just mixed up. So without inversion, so rho 1 is going to be what is that? I think it's okay. And in back here has the information there with rho 1 is okay. Delta x1 is here. Is the equation of alpha 2 divided b down to 1k e to the other k alpha x1 minus 2. I mean, this is essentially give you the delta. And then potential interaction term is the given the alpha b alpha k d k. It's just Fourier transformation. And plug that one into here. Plug that one to here. Plug that into here. Then what you get is an problem. potential potential. So that's what you get from this. Sorry, here, so it's a bit confusing. So that was alpha prime, and this is alpha 1. Okay, that's what. So here we just I just plug this value into here and do the integration. Do the integration. And use the quick. So the first term is B0. B0 is just coming from here. Which term? Can you see that? Is it okay? I mean, BT, we just plug that one to here, but now we need to set the here x3, x3, right? So therefore, row 1, x3, x3, you get the essentially, this is 0. Essentially, the alpha function of 0, you get that. That will give you the B0, only give you 0 into here. Okay. And then the second one, you just get this one. Second one, you get this. Is it okay? I mean, if you want, I can derive more carefully, but I think you. Is it okay? Can you see that? Row 1. Okay, maybe I can do a bit more carefully if you want. Okay, your question. Okay, I can do it more carefully in the second term. So, for instance, second term, it sounds like a So that's what you get. Is that okay? So I just plug everything into here. So this one is this part, okay? And this one is just B. Is that okay? Are you with me? Is that okay? Just plug that way to here. Plug that on B. Is that okay? Then I just change the change of label. The here K was T, K minus K prime. Okay, so I call it the I can tell it equal to campus state. Sorry, plus K. And then this may equal to sigma self alpha alpha 2. Okay, we can just write down like this. So that is exactly what's written here. The first term is the one I mentioned. I mean, I don't think it's necessary to write it down. Because I mean, it's just yeah, integration of full x3 we keep it down the k0. We just keep this. So that's it. So that's what you get. Oh, sorry, that's you. So this is the potential for after Fock potential for this plane wave case with interaction. Okay. And you can further solve. So this is the potential. And now we try to solve this one. The second equation. Okay. Second equation. So we put this one equal to here. And then plug that one into here and then solve it. Okay. Okay, let's do that. If you solve it, so that E K alpha is equal to K squared divided by 3m plus 1 to E. Like this. So plug this one into here. And phi q is also phi q is just plane wave. Phi q I'm degenerate. Phi q is okay. Phi q is also plane wave. So therefore, if you integrate over x2, you just get the constraint on k. Constraint on k. And then yeah, you just get this. plus what you get from this line word. And if you try to linearize for this the outcome, and I call this one is K. This is the actually F alpha prime, and the K is prime. I call this. Then this is called Landau F function. So that's the what Landau introduced. Landau F function. We call it this Landau F function. And then the variation of this energy is can be written in a column. So recall this. So this numbering operator n is a function of energy. Okay? Function energy. So this equation itself does not determine E exactly because n also depends on E. Therefore, you have to really solve this equation. Solve this equation. Fine. Okay, so that's like this. Okay, so then from now on, we are going to use this equation to derive lots of thermodynamic quantity like effective mass. From here, we get the effective mass. Density state. And the heat capacity. The calculation is almost exactly the same as the ideal, but with some modification. You need some modification. I think let's take a break at this moment, and then after the break, I will derive this thermodynamic quantity using this hardware configuration. Yeah, let's take a break. Let's take a break.
我也得看。就是这两个一起，他跟另外学，看他讲就是从这个接那个，就是的，所以变得那个，我就是直接可以提出来， 就是之前那个单为啥单一组的运动团成功矩阵少那组那个我觉得这个地方真是
这个没带东西就带。
那个本身方式。
对。啊，这个分数。
是吧？那个解还是从得到的那个n和一带到那个其中句式那个句式那个还表达是前提，别的从就是带到把那个解带到那个句式。
到这个这个。
啊，对，是那个。啊，这个可以我比较，就是把这个后面的这边就把这个带动这个这个。啊，对，应该是这个地方没有写过，有什么想法？也是。这是之前讲过的，
就这个，
就是我说我没有告诉你，那个啥经历，
你那个这个待会就那个换一个，
就2章之前，这个我知道。就是这几个都。应该是，就是把带到那个，就是那个，就是背景，然后就是这类背景。为啥第二个推导公式它跟讲义上写的？
必须推动它的高度。
就它跟讲义上写的很不一样。
然后之后是第一个封闭，是吧？
加入
这个还是第一。
对，这边是对的。
就像前边带进去。
啊，对，是他们要
然后就这段，
带进去的，就是他只要把这个东西带进去，再跟之前的比较，就会。
这种就带进去，是不是你直接带到这里面做这个的话？到时候我见它不能变得画出来变得
就是这个。
这个还刚好我推变。
这也可以前面不管怎么样，这个就是他不到的。然后，
你可以说这个东西，
写的这些分类里面就大概就是会。
So
这一个图里面完全都差，剩下的。
So this is the omega, and then so I use this one, and then this one we write everything. For instance,
或者他们两个变成一起，为什么设置一项职业分？
这样，
好，我先给。
这个会早一点。哦。
这里面就是
这个。
So what I do is okay, so
有些
这种不差长，只知道怎么收敛。首先它可以很这个积分这一份放在这个考里面，所以它其实就是积分3、3、2这个变成。其实这个就是系数是1等它。哦。所以它其实把原来这个哈密顿样这边不是2种，哈密顿样的是。这哈密顿这个这是正常的，你把它拆成这样。然后就变成那个，然后这一项里面的，就是然后把这个就是这个东西就是它这个减它的就是它因为这个赛是它的那个接的这个东西就是那个过客，你的这个就是认为就是把是它的这个，所以它这个东西才这样东西合起来的，对，就得到这个艺术性。这两项合起来的，而不是这几项。然后剩下的大分就是这样子。
I mean, just plug your hardware book. So this doesn't. You are free from oh. So you can derive this one. I mean, just plug this in here and you can show us the different people between first two. So essentially, oh sorry, I think I need my then all of the different equals satisfy five and then so then you know to different is equal to E2. Therefore, this is extreme and then five. The first line. The first line. And they do home implement all sides. And second one does This is alpha 1 alpha 2. Okay, shall we resume? Okay, let's resume. Okay, let's resume and then And then I think this is important, very important document, right? So this is already I already used this one to derive this cycle. And I want to keep this blackboard. So if you try to erase, please stop me. Yeah, if I try to erase that board, please stop me. Okay. So apply this Hartree-Fock equation to the low temperature ferment. Okay, low temperature ferment. And we know the low temperature ferment, so the chemical potential at the zero energy becomes Fermi energy. That's we know what it means. And then the number operator can be written as follows: sum of k alpha there at f minus k. So we the same thing. So even if zero temperature, even if interaction we have an f here, and then not very no further, and then this. And then, of course, in momentum space, you can just form this whatever. The state K3 are filled in a ball, and with radius with Kf, minus Kf. And this Kf can be obtained just number divided by d. So the density is just given by the normal state. Normal state in filling this situation. So therefore, essentially this is Q and Q. And then so sorry, what is the volume of ball? Is it 4 pi square?
Over 3.
Over 3. And you can add Q.
Yeah. There's no square. No square.
Huh?
No square. No square.
No square. Okay. Okay. No square on top. Okay, I think we need some normalization to get that. Yeah. Okay, so here, what is this? Spin is 1/2. So we consider spin 1/2 as is plus minus 1/2. So therefore, this is degeneracy 2. And I normalize like this way. You can normalize like this way. So this can give you that the Kf is equal to 3 pi squared and over d divided by and so one of them. So that's the Fermi momentum. So this is the valid. So this is valid for good interaction. with interaction. However, so epsilon k will be modified. Epsilon k will be modified by this interaction term, by interaction term. Now, one can write down this one is equal to half over k. Like this one, you can just say. But this one, the meaning will change. With interaction. The meaning will change with this interaction. I mean, the value of epsilon f will change because of the you put the interaction term in the Hamiltonian. But this one is valid for with or without interaction. Okay, let's consider the around Fermi surface. Will change like this way, and this one is equal to so recall the epsilon k. So it's a formula. Okay, so now for d epsilon k. D is equal to 0. But here, the M change, so this is the effective amount. Because by interaction term, the epsilon k will change from here. Epsilon k will change from above, like this way. Like this way. You change like this way. Therefore, so it's no longer true that the epsilon k divided by k is this one. So you have the effective amount. Did you understand what I mean? So here, epsilon k, according to Hartree-Fock equation, we will modify from this free particle. Okay? Therefore, if you take derivative k, it's no longer just standard mass amount. Here it's no standard mass. Because there's a bunch of the production term by interaction term, I just put everything, all the equations put into here as by x star. Okay, so then if you solve this one. Like this. Okay, so then the single particle density. So if you consider this one, you can just treat this one as before. As you recall, so this one I just insert. So 2f. So spin is now 1/2. But anyway, so L over 2 pi. Okay. Okay. And now I put the S to B. So S to be 1/2. So this is like this, become like this. So here, so as before, this one, I just put the delta K divided by delta K. I put that like this. And this is equal to. Okay, so that's what you get. Okay. So again, I use the equation of this one. So this one, but K equals to K, I just use this. So this is the almost equivalent. So this is with interaction, but with no interacting. As you recall, so D of E is just B K M divided by pi squared. So no interaction, we just have M here. But with the interaction, it becomes M star. That's the only difference. So all the interaction information is encoded M star. And I have to keep the other block mode in red here. And the rest of the calculation also same as before. You just change the M to M star. You do a computation. Okay. But this is D. Okay. So the rest of the calculation all the same. So for instance, heat capacity in the ideal gas case, D is equal to KV infinity, and D of E and then x plus what will it be? For so that's the heat idea. So we derive this one by using what was that? dE is equal to so this one is derived from E down S down T down S D. And plug the entropy formula into here, you can obtain this. But even interchange part is the same. So we should use same density of state. But the only difference is just replace M to M star. And if you do that computation, so this will give you roughly. So this is already derived as before. When t equals to 0, this is something with this one. And you can perform this. So when t equals 0, mu does not vary. Mu is said to be Fermi energy. So therefore you can ignore this one, and you just only need to consider this one. And then this one is equal to times mu increase something like around. Okay, so this one we already derived, but here we just df is different from the ideal gas case, only with you just replacing mass by effective mass. So now let's derive this effective mass by using this one, by using this. Okay, to derive that, so we use to derive the effective mass, we use the second hundred of the equation. So suppose delta K is something like minus M Q M times U. So U is some vector, you can answer. Then under the deformation variation, you get this one, which is equal to, so we already know this one is equal to minus K. And also. Okay, so the plug them into here, and you raise the so plug this one into here. Let's plug this one into here. And what you get is common. Like this. Okay. So I just use this relation to apply this one and just get rid of u. That's what I do. And you get it. Okay. Okay, so so suppose K is near the Fermi C. So the Kf, F, and this is okay. This is Kf. And then we just multiply the K, so multiply Kf over K squared. Then what you get is the following: 1 over m star. Like this. So what is the delta function here? Can anybody answer? So recall, so this one is essentially we have the function. And if you take a derivative, you get a minus down. That's what. Okay. So now we'll do the same massage as before. So here, if you have a delta function, you can massage this one by like this one, using this trick. Sum over k and it can be replaced like this. And then what you get as follows. 抓主角。So the first integration, so it just gives you the condensing. So the first integration is just this rough approximate by this much. So you get the negative state, negative state above from this factor L to the cube. L to the cube. Oh, L to the cube. You have to work on it. And the rest is the angular momentum. So angular momentum. So here, as you can see, so this depends on so note that this d omega is the angular momentum integration. And the assumption this is only depends on angular momentum. No, angular dependence. And also kf of k prime is also has only angular. So what we have is a here, a prime here, and then you have a k prime of k f. That is the only depends on here, state and point. So those functions and this function is only depends on angular momentum. So you can perform this radial direction to get that to replace by this density state. So at the end of the day, so you get that this is equal to 1 minus of f of v of alpha prime and d omega prime. Like this. Now, so we will see how this depends on. You can just write down like this, equal to 0 infinity and that's L L A over 2, and then this is independent phi, so you can define rotation capacity. Here it's just to have a further harmonic. Legendre function. So this is a function. So here, this parameter is called. So these parameters are called Landau parameter. And we will derive this parameter later, but we just assume this is a function and another function f. Formula function. So the Legendre function you already encountered in quantum mechanics. Quantum mechanics. So one need to. Okay, maybe I can just write down. I mean. Okay. The general definition. Like this. Okay. Okay, so we plug this one into here and do the integration. So plug that one into here, you get the so m over n star is 1 minus sum over L is equal to 0 to infinity, and the sum of alpha prime is equal to plus 1.5, and Ls minus F of A divided by 2 plus delta of alpha prime F L A, and the integration variable T omega prime 4 pi P L cos theta prime and P1 cos theta prime and M over M star. So recall that here, this guy is can be written P1 of cos theta prime. It's just P1 of cos theta prime. So I just replace. And this general polynomial is the orthogonal function. So orthogonal function means that so if you and you get the delta L prime and with some normalization factor 2 over 2 L prime. That's what you do. So orthogonal function. Therefore, this integration just only kick out L is equal to 1. So everything becomes L equal to 1. Okay? And then what's left is sum over alpha prime. Okay. So if alpha prime is the same as alpha, you let me think. Sorry. So L becomes 0 and this is equal to 1 minus. When alpha is alpha prime, you get that this is equal to 1. Okay. This is equal to 1. So you get the FL divided by 2. And this is equal to 1. Means that the on the other hand, if alpha is not equal to alpha prime, this is 0. So therefore you have FL S minus FL A divided by 2. Okay. Therefore this is equal to okay. This is again. So everything wrong. So everything wrong. And then A part cancel each other. So now what you get is D. So that's what you get. Okay. Now from here we can derive the effective mass sum of n is equal to 1 plus x1 s divided by 3. So that's very simple. So all the calculation is very complicated, but at the end of the day, so you get that very simple formula. So that's what Landau's genius. So this is the what Landau did for 1950. So this is the effective mass. And we can do the same thing, simulate relation between interacting part and non-interacting system by using the source Landau parameter. The source Landau parameter you can use. So now I can erase here. I don't think it's a good idea to do that. So I think let's keep it. Then but I want to calculate. So this is one of the most important identity I wanted to derive today. This is a main equation. Now I think I can keep this one. So except the origin here. Okay. Okay, so the next is so for the spin. I don't know. In Japanese, it's called super. Do you say? So this is just a So suppose you have a magnetic flux density P is here. Okay, so that's okay. But if you turn on the interaction, so this will just multiply delta epsilon k, alpha plus mu m, alpha. So this is without interaction. And with interaction. Okay, and we want to understand the relation between susceptibility with zero or without zero. And we can use again after pocket question, something like this. It's the same thing. Same as before, like this. So we should write down the same equation. Like this way. And now we can use same trick as before. Same trick as before. But now here there's no such a term. So there's no this kind of term. So we just have the integration is we want this term become P1. But there is no such a term, so we have to use P0. Okay, then if you use this one, what you get is that the integrations are follows. So this is essentially equal by mu m0 alpha minus PFL S minus delta X divided by G delta alpha for current. And then FL and then P L was there prime and P0 was there. Then the omega prime or phi. And the mu and alpha prime. Okay, so that's what you get. But now, here you have alpha prime, and you have to sum over alpha prime. Okay, alpha prime. At the end of the day, so alpha prime is plus minus 1. So alpha prime is plus minus 1. Or 1/2, okay? 1/2. So instead of here, so here instead of plus, you get minus in this case. So therefore, the S cancel and the S survive. S cancel. And at the end of the day, so to do this computation, I can ask you. So at the end of this explanation, Okay. Here. Okay, that's what you do. Fine. Okay. This is also important. Okay, so magnetization N is given by B, C, M, zero, alpha, rho, one, C. Okay. So this will become something like this one. So this will become something like a sum over N alpha, mu, and zero, alpha and bottom, N and R. That's what you get. And this is equal to, roughly speaking, this is equal to K alpha mu m zero alpha. And then del and R, K, and del is to K, del is to K. We'll do the same thing before. So del is so K is now this the black on here, and this is equal to zero m b sum over sum over alpha. This way, and this is equal to moving on back. Okay, so this is monetization method, and then susceptibility function del P is equal to divided by fine. Okay, that's my susceptibility. And of course, for ID gas, what would you get? ID gas. Huh? In the case of ID gas, what is cup? It's only numerator. Numerator. There's no denominator. Okay, that's how it works. Okay, we can do the same game. We can So this is another important equal. Okay, and the next is complexity. This one, in Japanese, most likely like this way. Anyway, I don't even remember how it's written in Japanese. Is it same? Okay. Are they yash? Yes. Okay. Okay. Yep. Which is and if you do the manipulation or using thermodynamic quantity, what you get is that the at t equals 0, low. So I'm working on all low temperature, so really low temperature. And this is equal to like this. And the next goal is to derive sorry, I'm doing something stupid. Sorry. I'm doing something stupid. Okay, I'm running out of time. So sorry. So from here one can just have 1 over kappa is equal to n squared b down mu and then down f. That's what you can do. So by using some quantity. And what you need to do is that the relation between del n and then del mu. Yeah. So just because small. So this is equal to sum over k after well and bar k. And this is equal to sum over k after del and bar del mu plus del and bar del additional k del additional k. Plus, and this is equal to sum over k after like this. Not like this. And this is equal to E of 2 F. And then del mu minus del epsilon k. And what we need to derive is from delta from K. And do the same thing. It's really the same thing. Same as before. I'm going to be this class because it's the same computation. So if you do that del epsilon K, so del epsilon K is still over B, M over K prime, alpha prime, is alpha prime, K and K prime, del and bar. Then do the same exercise as before. What you get is that the same answer as before. This is equal to let's and here again you have this integral PL and P0 dx. 1 minus 1. That's it. And then the same reasoning, what you get is that this will equal to F0 S D is from K and sum over K. Oh, sorry. Prime of 1 down and from K, which equal to F0 S D F. Yeah. Okay. So now we know the relation between del epsilon K and del N. So plug that into here, one can derive so this is new. Probability for K, and this is equal to 1 plus F0. So the first divided by B plus F0S divided by B epsilon. That's what. By using this relation and this relation.
上那个代码的话，
那好。Okay, so that's good. So this is another important. Okay, so like this, even with inflection, if you use this Hartree-Fock equation, and then use this expression of the Landau f function in terms of the engendered polynomial, one can everything write down all the simultaneous quantity by just using this Landau formula. That's the essence of this lecture. And then let's derive, so Fk, suppose if Fk has a following assumption, okay, then maybe next time I will briefly draw this one. If V M of K prime, I'm running out from F equal to 0 infinity, I'm sorry, it's running out of time. Okay. So if you write down this in terms of this Legendre term polynomial, Ls is given by this function, e epsilon f to e to delta L field minus 2L plus 1 and then FLN also can be written like this way. Anyway, so this is the same as Fourier transformation. I mean, instead of e to the minus e to the I k x, I just expand by the general term. And its Fourier coefficient is given by here. Given. Then the FL and the FLS, FLA can be written in terms of this Fourier coefficient. Okay, let's stop here. Okay, so this is let's stop here, and then next week. Okay, so tomorrow there's no lecture, of course, and then the week after I'll be back. So move to as usual. Then we'll talk about the superconducting.